Hi folks, we're going to do a little calculus problem here. It's called related rates. It's a little complicated to think about, but it's really easy to do. That's the good part. Right now I have a rock, I threw it in a pond, and it's causing some circular ripples to expand out. Now if we can imagine those circular ripples expanding out, you know that they're going to move outward at what we call linear velocity. That linear velocity is 4 inches per second. So it's traveling outward 4 inches per second and expanding. Well, there's something else that's changing. The area of this thing, if the radius is moving outward at 4 inches per second, what's happening is that as the radius gets bigger and bigger, the area expands a little bit faster because the area is being, the radius is being squared to find the area. So it's expanding even faster. There's a relationship between those rates. Now the way we solve the problem, it's really easy to do. We just look at how area is related to the radius. The area of a circle, these are circular ripples, is equal to pi r squared. Now what we're interested in is looking at the change in the area over time. And in this case, we're going to differentiate both sides of this relationship with respect to time, d dt. What's going to happen now is that I'm going to have on this side the change in area over time. Now remember that this is the instantaneous change because this is a derivative. Over here, I'm going to take the derivative of the radius with respect to time. So I'm going to multiply the 2 times pi. That's the exponent times the coefficient. I'm going to reduce the exponent by 1. That's the radius to the first power if you like. And I also have to take the derivative of the radius with respect to time, dr dt. Well, here's the thing. Like I said, this is really easy to do. You see, this is dr dt. And there's the radius of interest. I want to find out how fast is the area changing when the radius is a half a foot. Well, I can't use this. I have to use 6 inches. And I can substitute into this equation. dA dt is equal to 2 times pi times the radius. This is 6 inches. And dr dt is how quickly the radius is changing over time. And the radius is changing over time at 4 inches per second. And what I end up with is 2 times 6 times 4, which is 48, pi, and this is inches times inches is inches squared per second. This is the rate of change of the area when the radius is half a foot. Now I can actually verify this arithmetically. We just use basic arithmetic. We can look at this and see what happens. Here's my rock, and my ripples expand outward. These are supposed to be circles. And the area is changing, just like the radius is changing. Well, at some point in time, at this point in time, my radius is 6 inches. And what we're going to do is we're going to look at what happens one small instant later. I'm going to look at a change in time of 0.01 seconds. In other words, I'm going to look at what happens between here and when the radius is at 6.04. You see, the radius is changing at 4 inches per second. That means that in 1 second it goes 4 inches, so in 0.01 seconds it goes 0.04 inches. So in that 1/100th of a second, my radius expands just a little tiny bit. There's a little tiny change here. And what I'm going to do is I'm going to look at the change in my area over the change in time. Now to do that, I have to find the area. Now the area at 6 inches is easy. That's 36 pi. At 6.04, I'm going to have to do the multiplication. Now when you do this, don't just grab your calculator every single time you have to do a basic calculation. It's a good idea to go ahead and grab your margin, in the margin of your paper. Take your 6.04 times 6.04, do a basic arithmetic. That is 6 and 1 and 24 and 0 and 0. Don't forget the 0 here. And that's a 4 and carry the 2 and 36. And when I add this together, I have to move my decimal 4 places. 1, 2, 3, 4. So I get 36.4816 times pi, because I want pi r squared. So here's what happened. The area of this ripple was 36 pi. After 1/100th of a second, it's 36.4816 pi. It's not very much bigger, but just a little bit. So what we're going to do is we're actually going to take the rate of change. We're going to look at it arithmetically. And I'm going to just take that change. I'm going to take the change in the area, which is 36.4816 pi minus 36 pi divided by, now I'm going to look at my time. My time was, the change in time was 0.01 seconds. This is the change in time. I do the subtraction and I get 0.4816 pi divided by 0.01. This moves my decimal 2 places. One way to think of this is I'm actually multiplying by 100 over 100. Some people have a little trouble simplifying decimal fractions. Take a look. Multiply by 100 over 100 and I get 48.16 pi. What? Well, this is inches squared per 1 second. Now this isn't an exact answer. This isn't an instantaneous rate of change. This is the rate of change between 6 seconds, between the time that it's at 6 inches and the time that it's at 6.04 inches. The time itself is actually, since it's moving outward at 4 inches per second, it's actually 1.5 seconds. It's between, this time period is 1.5 seconds, and that's when it's 6 inches, and 1.51 seconds. And when we subtract those, we get our 0.01. I didn't want to confuse the issue too much, but basically, since it's moving outward at 4 inches per second, it's at 6 inches at 1.5 seconds, or 1.5 seconds. What I've done then is find the rate of change between 1.5 seconds and 1.51 seconds. The instantaneous rate of change at 1.5 seconds is 48 pi. Inches squared per second. Hopefully it wasn't too confusing. Like I said, it's easy to do. A little more difficult to verify, but you want to be able to think about it a little bit. Next time I'll do a balloon problem, and we'll do related rates with that.